Okay, can everyone hear me? Yeah, so I apologize for the delay. So we're doubly delayed here, so I'll try and keep it fairly short. I know everyone needs to get to lunch and we need to keep on time, so I'll try and keep it brief. So let me just say, first of all, it's an honor to be here to honor Professor Smale, and thank you to the organizers, Indika and Michael and so on, for inviting me. So there's an interesting connection. So I'm, of course, from the University of Michigan, as is Indika. And Professor Smale, unfortunately, is not here at the moment. But anyway, he was an alumnus of the University of Michigan. He got his undergraduate degree and his PhD there. And so there's a very nice connection with the University of Michigan. I believe tomorrow there'll be more about the University of Michigan, about its fame and infamy, or whatever, either way. So you'll hear more about Michigan tomorrow. My collaborator on this work also has a connection with Michigan and with Berkeley, in fact. So Tudor Ratiu, that I did this little bit of work on the Monge-Kantorovich problem, was actually a postdoc at Michigan. He was actually a PhD student here at Berkeley. And originally, in fact, he came wanting to do his research with Professor Smale. And, you know, Professor Smale, Steve, was working on mechanics just before Tudor arrived. And this hasn't really been mentioned, but there was this beautiful work on topology and mechanics, and the work on the amended potential. So I think Tudor actually arrived at Berkeley hoping to work with Steve. But as you know, he's lurked on lots of different things and he'd moved on. So when he spoke to Steve, he said, you should talk to somebody else, and in fact advised him to talk to Jerry Marsden, which he then did, and Tudor worked with Jerry. But in any case, there's this other nice piece of work on mechanics, and the amended potential and related things has played a big role in the work on mechanics since then. So anyway, what I was going to talk about today is this work on, which also relates to other parts of Steve's work. So I've called it Dynamical Systems, Linear Programming, and Monge-Kantorovich. So Steve did a lot of work on things related to that, and I'll say more about that in a moment. So what I'm going to say is a little bit here about the Monge problem in finite dimensions, and how it relates to some work that I've done over the years, actually, partly with Tudor and partly with other people on dynamics and linear programming, how it relates to the Schur-Horn theorem, which is a beautiful theorem in linear algebra. Sorry, let's see if I get that. See, can I get this? No, actually, that doesn't seem to. Okay, anyway. Seems to want to move along. And I want to, so the Monge theorem in finite dimensions, and you can also relate it to the infinite dimension Monge problem in a rather interesting way, which relates to some of my work on integrable systems. So I'll say something about that. Just a couple of little pictures here that relate to the talk. So this is the famous Schur-Horn polytope I'll talk about. So that's related to this work on linear programming, but it's also related to mechanics. In fact, the so-called momentum map. So that plays a central role here. And this is a little twist of it that refers to what happens when you look at the total lattice on tridiagonal matrices. I probably won't have time to get to that today. So, so here is a little bit of this. So this is some of these strands that are reflected in Steve's work that I want to talk about today. So first of all, you know, my introduction, I guess, to Steve's work on dynamics was this rather beautiful book, The Mathematics of Time, which many of you have looked at. And so that was how I first thought about sort of dynamics in some sense in the Steve Smale way. And the strand that this work that I'll talk about today brings together are dynamical systems, which of course Steve played a big role on. The other thing that is important is linear programming. So Steve did this great work on the complexity of linear programming. So that comes into this a little bit through these polytopes that I just mentioned. It's also related to economics in some way, the Monge-Kantorovich problem. And again, Steve was interested in that. And then the other thing that he's been interested in recently is biological systems and networks, and this is something I've been working on with Indika and other people, and kindly supported by Fred Levy, who's here. So this is introducing dynamics, mechanics, all these interesting tools to biological things, which is something I've just learned about recently. So I know whatever I know about biology, basically I learned from Indika, so that's been good. All right, so here I want to talk about how some of these strands come together in the Monge-Kantorovich problem, and as I say, I'll try and keep it fairly brief, as I know we're running late here. So the Monge-Kantorovich problem is the problem of mass transfer. So this is a famous problem which a lot of people know about, of course, is how you transfer mass from one point to another in an optimal way. there was a rather nice paper by Brazis in 2018 which described it in a finite way. And I want to mention that fits rather nicely with the work here. So I want to describe this finite dimensional setting and how it relates to some of our work. And then also look at the problem in infinite dimensions, a very particular case of it, which relates to some of our work on PDEs and the relationship to a sort of infinite dimensional version of the Tudor lattice problem. And so this relates to the infinite dimensional Monge-Kantorovich problem. And you can read about that in lots of places. And in fact, Larry Evans has written this rather beautiful book on it. And that's one place to read about it. And there's also the work of Gambo and McCann, who I've discussed this with. So anyway, as I said, we'll relate these problems to the Schur-Horn theorem, to this infinite dimensional generalization, to some other work that I've worked on gradient flows. So let me just say something about that. So I'll mainly stick, just in view of time, to this finite dimensional setting. So this is a sort of simple computational problem in a way. So you just consider a bunch of points. And this is basically linear algebra in the sense that Professor Chua just discussed it. A lot of this is all linear algebra, which is not to be underestimated. So I have a bunch of points, pi and ni, x and y over there, and a cost function, which is just a cost function on the pi's and the n's. So basically you're looking at minimizing sigma I equal 1 to n of the cost of pi with some permutation of the n's. And you're trying to put those points together in some optimal way. So here, S is just the permutation group which acts on these points, all right? And if you set K to be the minimum of these things, that's sort of essentially the Kantorovich problem. You're just minimizing sigma Aij, Ci, Pi of Nij. So the Monge problem is just minimizing this over various permutations of P and N. And the Kantorovich problem is a slight relaxation of this, where you throw in this doubly stochastic matrix, which plays a role in the Schur-Horn theorem. And then you can also formulate a dual problem. So that was the big contribution of Kantorovich, is that you could go from this Monge problem to this Kantorovich problem and then to this dual. And that turned out to be optimal for solving these kinds of minimization problems. So the details here aren't too important, but basically you're just minimizing a cost function between these points and these permutations. So I'll say something about how that all works together. And what you can prove that these three problems are basically are identical. You can prove that minimizing M is the same as minimizing K, is the same as minimizing D. And you can see it basically through this Schur-Horn theorem, which I'm going to mention in a moment. So basically, what Brazis does in his paper is he goes through a bunch of necessary inequalities, which basically end up giving you M equals K equals D. And I'll say something about how you do that here and how it relates to some of our work in dynamics. So this is related, as I mentioned, to dynamics in the following way. So here is a problem which is essentially equivalent to that, and it's kind of a fun thing to think about, and it's played a role in various bits of things that I've worked on. So you just consider minimizing the function, let's see, okay, sorry, I'll get this. I better stick to this, I guess. So you want to minimize the function trace Ln. As I said, it's a simple linear algebra problem. So I fix a matrix N, and I have, let's make it, say, skew symmetric or even diagonal. And I want to minimize the trace together with the matrix L. So I want to minimize trace Ln over matrices L, which are symmetric and have the same set of diagonal, at least have the same set of eigenvalues. All right? So that's a minimization problem. And you can formulate it in the following way. I want to minimize the distance between L and N squared, sort of similar to what I just showed you. So I take the inner product, minimizing over theta, L minus L, L minus N, which I can rewrite like this. So I look at the minimization problem over all matrices L that have the same eigenvalues as some given matrix. So it's kind of a simple problem. It's just minimizing theta transpose lambda theta over theta, looking at this inner product. All right? And so theta here you can think of as a unitary matrix. And this is really the Monge problem in this setting. And there are a number of ways you can do it. You can try and do it computationally. But one way to do it is to look at the gradient dynamics. So you can link it to dynamics in a nice way. So I look at trace Ln, and I look at the gradient dynamics on this orbit, the adjoint orbit, U theta transpose lambda theta. And this gives rise to a beautiful flow, actually, which is we call the double bracket flow, So it's the flow L dot equals L bracket n. And you can show that this moves to the minimum of this problem. And this is a sort of fun flow to think about. It's a flow on, if you like, symmetric matrices L. It's an isospectral flow. That means it conserves the eigenvalues. And the matrix N is, in fact, if you take it to be a diagonal matrix, the only equilibria occur is when L and N commute. All right? If you're looking at isospectral flows, that means that the only possibilities for the matrix L was that L be diagonal, it has its eigenvalues on the diagonal, and you can have any permutation of those eigenvalues. All right? And that's the connection with the Schur-Horn theorem and the Monge-Kantorovich problem. So let me say a little bit more about that. So this sort of encapsulates the theorem. I take the gradient flow of trace Ln with respect to the normal metric. That's the metric I just showed you. For n with its distinct diagonal entries, L having initial condition with distinct eigenvalues, there are these n factorial equilibria corresponding to these rearranged eigenvalues. And there's just one stable equilibrium. So there are all these other equilibria which are unstable, but there's one stable equilibrium, and you flow to that one. All right, so that's the theorem. And it relates to convexity in this rather beautiful way and to the Monge-Kantorovich problem. So let me say a word about that. So let's take just a vector in Rn, x1 through to Sn, and let the permutation matrix act on this. So I take all the permutations of n, and these are the theorems that make up the Schur-Horn theorem. And this is a rather beautiful piece of linear algebra, which is one of my favorite theorems. So what is the Schur-Horn theorem? So I take A to be a symmetric matrices with eigenvalues lambda j arranged in non-increasing order, and let lambda be the eigenvalues and the AIs be the diagonal entries. And then you can show that the diagonal entries of the matrix lie inside the convex hull of the permutation of those lambdas. So I take a given eigenvector, lambda 1 through to lambda n, I take all its permutations, I get a polytope, and Schur tells you that the vector of diagonal entries lies inside that polytope. And Horn's theorem, so this was Schur's theorem back in 1923, Horn's theorem, which is in 1954, tells you that map is onto in some sense. So if I take a polytope, let me just see if I can have a picture of the polytope here. So I'll come back to this, and this is another way of writing this. So the Schur theorem tells you if I take the eigenvalues and I take all their permutations, the diagonal vector of diagonal entries lies inside the polytope. And Horn's theorem tells me if I look at this polytope and I take any point inside it, there is a Hermitian matrix with those eigenvalues and this particular set of diagonal entries. So that's the Schur-Horn theorem. And it's a rather beautiful theorem. There's another way of thinking of it. Looks like this. If I just take the diagonal entries d1 through to dn and lambda 1 through to lambda n, sequences of real number arranged in non-decreasing order, then you can see there's a Hermitian matrix with diagonal entries d1 through to dn and eigenvalues lambda 1 through to lambda n, if and only if this set of inequalities hold. So d1 is less than or equal to lambda 1, the traces are equal, and all the in-between entries, d1 plus d2 is less than or equal to lambda 1 and lambda 2. So those are the Schur-Horn inequalities. And this set of inequalities is equivalent to that sort of convexity condition. So that's Schur-Horn theorem. And this has sort of played a huge role, in fact, in mechanics and dynamics. It's the basis for the theory of the momentum map and so on. So it's a lovely little theorem. And and there's another way of expressing it. So that set of inequalities, we say that the vector lambda majorizes the vector d. So that's called majorization. And there's a whole book about majorization. This is a simple example of that. All right, so that's the picture. And this is also related to the theory of doubly stochastic matrices. So we say a matrix is doubly stochastic, basically, if the sum of all its row entries and column entries is equal to 1. And you can show that a matrix P is doubly stochastic if and only if Px is majorized by x for all x. And moreover, the set of doubly stochastic matrices is the convex hull of extreme points, which are basically the permuhedron matrices. So that's really where this convexity comes from. And So I won't go through all the details here, but and I know we're sort of running out of time, so I'll try to stop now. So I have quite a few more slides, but I know we should stop. So I won't go through the proof, but what you can you can prove the Schur theorem and the Horn theorem quite nicely through the theory of adjoint orbits. So I'll skip that, and you can generalize this to other more sort of, this is all square, you can generalize this to other more complicated Monge-Kantorovich type problems. But basically, you can use this, the gradient flows and this theory of convexity to prove this Monge-Kantorovich, these results, m equals k equals d, in this nice sort of unitary group setting. And since we've run out of time, I won't go through all of this here, but there's a beautiful infinite dimensional generalization as well to the group of measure-preserving transformations. So you can do this all using measure-preserving transformations and get an infinite version of the Monge-Kantorovich problem, which also brings, in a very nice way, dynamics in infinite dimensions and links linear programming in an infinite dimensional setting to dynamics as well, which is, again, reminiscent of Steve's work. Okay, so since I know everyone wants to get to lunch, I think I'll skip that part. I'll just leave it here, and thanks again for giving me the opportunity to speak.
Thank you so much, Dr. Bloch, and the lunch. I want to remind you, 4 o'clock, we have a bus here to go to Dr. Smale's house. So please come, everybody. And the bus, and who has a car, it's okay, but if you like to go...
4 o'clock?
4 o'clock, 4 p.m. Yeah.
From here.
From here, yeah.
Okay.
Yeah. I will show you and we will go, but please come everybody tonight. And Dr. Smale is so excited to show his minerals and have a good time tonight. Dr.
Share the address. Could you share the address?
Oh, sure. Yeah. Yeah, I will send this. You come separately.
Later. Don't forget to remind people when we continue.
Oh.